So thank you all for your intellectual endurance. We've heard a lot from philosophers in this session and in this conference, but a new breed of philosophers who are informed by psychology. And likewise, we're lucky to have some psychologists among us who are very philosophical in their orientation. When Edouard and I agreed to do a conference on perception and concepts, no one else seemed a better fit than our next speaker, Rob Goldstone. Rob actually heads up what's called the Concepts and Percepts Lab at the University of Indiana, one of the very fine psychology and cognitive science programs in North America. He has been the director of that program as well as the chief editor of the Journal of Cognitive Science. So Rob is kind of not only Mr. Perception and Concepts, but Mr. Cognitive Science. So he's a tremendously representative figure and a very accomplished one. So I'm no mathematician, but reading through Rob's Vita is a little bit like reading a Tolstoy novel. It goes on, and by my count, there are something like 200 papers. Let me say that again, 200 papers. I started to calculate, how long I would have to live to catch up to Rob, which was an interesting bit of mathematics. I did some other mathematics. I realized that a single sheet of paper, maybe 3 sheets of paper, would make up something like a meter in length. So if you think about each paper at about, say, 20 pages, that's about 1,333 meters, which would probably, if lined up, get us halfway around Riga, maybe farther. So this is a tremendous amount of environmental damage. These papers have been a source of inspiration, education to me personally, and I'm sure to many in this room. It's always a special treat to be able to expose philosophers to psychologists whom I admire, and I'd be thrilled to discover that there are some people in this room who have not waded through all 200 of those papers, because I'm sure after listening to Rob, you'll realize that you know what you need to spend your time doing over the next months and years ahead. So it's a tremendous pleasure to introduce Rob Goldstone to you.
So thanks for that overly kind introduction, Jesse. I don't think I'll be able to live up to it now. I'm up here, so my arousal level is high. I don't know what the rest of you are going to do, though. I would like to talk about an issue that's been of interest to us for a number of years now, which is what is the relation between formal reasoning, high-level cognition, and our perceptions, which I think is obviously one of the core topics that many of the people in this room have talked about and grappled with over the years. And by one account, the relation between the two is one of adversary. Right? So there's both philosophers and psychologists who seem to have a view in which perception is at odds with what you would want by formal cognition. So Quine has said that it's the hallmark of an advanced science that it no longer requires notions of perceptual similarity, right? It can just use the special terms within the science in a formal, rigorous kind of way. Sue Carey has talked about how there's a developmental process in which the infants start off being theoretical, but they're more perceptual also. And development can be understood as a regular progression of dispensing with some of the unsophisticated perceptual skills and developing more nuanced theoretical grounds for the inductions and for the categories that the child makes. Steve Sloman has talked about about pitting System 1 versus System 2, which has been popularized in the work by Danny Kahneman on fast thinking and slow thinking. You get this idea that there's a real tension between these two views. Our perspective is going to be almost the opposite of that. We're arguing that perception and cognition can actually fit more hand in hand, largely because perception can be tailored to fit the needs and goals of higher level cognition, the goals of our formal thinking and our formal needs. So our perceptual system is not doomed to always give us a certain set of similarities. It is itself tunable. So perceptual learning is extensive. It occurs at multiple neurological and functional loci. It doesn't all occur one place. Some of it is very early in areas V1, V2, V4. Some of it is much later. It won't be all painted with the same brush. So the point that I'd like to be making is that you can actually adapt perception to fit your needs, to do the right thing, whereas what we mean here is not doing the morally right thing, although that'd be an interesting extension of this that I think Jesse is pursuing. But in this case, it'll be doing the right formal thing. And so by this account, you can achieve formal abilities, formal skills, not despite perception, but actually through perception. And in this sense, the talk that I'm going to be giving is going to be cut from the same cloth as the preceding talk by Dr. Noe. This will be the psychologist version, maybe. So I'm going to start off by giving a case study of this from algebra. The reason for studying algebra, which is here, can anybody see what is up there on the board? No, okay. Look, okay, good, thanks. I was just waiting for one person. This is to you. So we're talking about algebra because algebra is perhaps the paradigmatic example in Western civilization of formal symbolic processing. Natural language is far too messy to be considered strictly formal processing, but at least in the Western civilization, algebra is the last example of symbolic reasoning that many of us get to. Right? And researchers have argued that mathematical reasoning is based on perceptual models or spatial imagery rather than formal symbols. Right? And there's something to the dialectic of folk like Lakoff and Nunes that would say that you have these concepts of mathematics that are grounded in embodied felt metaphors versus what you would get from pure symbol grounding, from pure, not pure symbol grounding, pure symbolic pushing around, right? Manipulation of symbol systems. And they're arguing that oftentimes you get a more generative system because it's based upon these experienced metaphors rather than this symbolic processing. However, what we'll be arguing is slightly different, which is that even symbolic forms have analog, spatial, perceptual properties that can influence their processing. And so I think there's something which is missed by this dichotomization of grounded versus symbolic, which is that the symbols that we use, that you can actually point to in algebra, are actually grounded themselves. They're grounded because they're given by notation. Okay, so here's a warm-up example to make sure that you all stay awake. To yourselves, actually calculate the answer to this. This is not a Gedanken experiment. Actually come up with a number. Okay. Okay. Well, that's part of the question, right? So I'm getting a lot of answers for 2. So how many people, by raise of hands, come up with the answer 2? Lots of people. All right. How many people come up with a different answer? 1, 2, a smattering. We'll say 5%. What was your answer? 4. Okay, interesting. Any other answers? Okay, good. Yeah.
I originally had 4 and we got 2 because the last.
Oh, right. Exactly, right. So there's different types of confusions, right? So actually, interestingly, none of you did what would be considered the formally right thing by mathematicians. So the formally right thing is that we do have an order of precedence, right? You have to follow PEDMAS if you learn it at school, parentheses, exponentiations, division, multiplication, addition, subtraction. But when two operators are tied for the order of precedence, like multiplication and division are, then in our mathematics that we're using in Western civilization, then you have a left to right order of evaluation, right? So the correct answer is 5 minus 1, 4, times 4, divided by 4, so that's 4, and now times, whoops, 2, times 2, oh yeah, that's 8, right. So that's the correct answer, but many of you give 2 as an answer, and you would get 2 by basically creating something like this as your structure. So I'm guessing that's what you'd do. And it turns out that the reason why you're doing that is because you're influenced by a perceptual, maybe aesthetic property of balance. You like to have 2 things in the numerator, 2 things in the denominator, right? And you can show that there is this aesthetic feeling of balance, because if I had given you a problem like the one here, then you could show that people are much less likely to put the 1 plus 1 in the denominator. They're much more likely to put the 1 plus 1 in the numerator, because there's such an apparent difference between the 2 square terms and the 1 plus 1 term. So people are influenced by this perceptual, Gestalt principle of symmetry when they're doing formal symbolic algebra. We give our students problems that are much easier than this because they're not sophisticated philosophers. So what we end up giving them were very simple problems where we manipulate the spacing, right? So we give problems like, what's 2 plus 3 times 6? And I was trying to emphasize with my pause of voice what the physical spacing is representing. So here we have a big physical spacing around the plus sign. We have a small physical spacing around a times sign. This would be considered consistent spacing because it would make people perceptually group things in the same way that they are actually grouped according to the order of precedence, whereby multiplication takes precedence over addition. All right? Here's an inconsistent, tricky one, where 2 plus 3 are closer together and the 6 comes later. And that is something that would incline people to do the 2 plus 3 operation first, giving, in this case, the wrong answer of 30. 2 plus 3, 5. 5 times 6 is 30. That's wrong, but that's what you would get if you're influenced by physical spacing, which our subjects are. So you can show, regardless of the difficulty of the problem, as evidenced by the magnitude of the largest operand, which does have an influence, people are also going to be very highly and systematically influenced by the consistency of the problem. So they're always worse off when the physical spacing is at odds with the formal order of operations. And this is despite the fact that these are simple arithmetic problems. We give subjects trial by trial feedback. Every trial we tell them whether they're right or wrong. And this is, the subjects in this case were undergraduates who had to have finite algebra before they're taking the course that we were testing them in. Okay, so here's an example of other perceptual grouping pressures that David Landy and I have explored. The one that I was just talking about is physical spacing in a slightly different situation where subjects are asked to say whether the equation is valid, whether it has to be true for all values of the variable. In this case, the equation is not valid because we have a z times t term here and we don't have a z times t term on the other side. But if subjects are misled by the physical spacing here, then they would say, okay, I got a f plus z group here. Okay, I got something like an f plus z group here. I got a t plus b group here. And I have a t plus b group here. All right, I guess they're equal. Bah. So we give people, again, trial by trial feedback telling them they're wrong. The physical spacing effect that I just talked about is whopping large. Subjects are 6 times more likely to make errors in the inconsistent spacing version of this than the consistent spacing version. But that's not the only kind of influence that you can show. You can show an influence of what Steve Palmer and Irv Rock would call common region. Just putting in these triangles above and below the mathematical equation makes people far more likely to get the wrong answer if they're inconsistently grouping with the order of operations, right? The same thing with connectedness. If we put these lines connecting the terms above the n plus b elements, then subjects are much less likely to get the right answer than if you put the bars above the b times m term. That would be consistent. So connectedness and common region, also very strong effects. Other interesting effects, we have an influence of alphabetic spacing. So the proximity in the alphabetic order, ABC, influences people's judgments so that people are more likely to group the A and the B together because they occur closer in the alphabet. Or maybe they're more semantically related, but just in terms of the letter itself. So people have a hard time grouping the B and the X because they come from opposite ends of the alphabet. That's a smaller effect, only about a 4%, still highly significant, but this is definitely a smaller effect than the physical spacing effect. The other kind of effect, which is also subtle but true, is an influence of the structure of the equation itself. So we can make one term be a variable times itself, and the very form of a variable times itself makes people want to group it with another variable times itself, rather than a constant times a variable. So people are influenced by structural similarity in grouping these objects together. This is not how you would want to build Mathematica. I don't think, that's not how Wolfram has it. This is not how you express mathematics to students. It doesn't matter what the variables are. They're variables, right? But people are very influenced by the nature of a variable, as any physics student will tell you. If you make time so it's not t, but it's r instead, you're going to drastically increase your students' error rates. All right. Okay, so the results, I think, are pretty compelling. The interpretation is not as compelling, right? So there's 2 different types of account that one could give of this. One account is, hey, this is just another case of formal and perceptual strategies producing different results. You could definitely frame it in terms of Sloman's ideas of system 1 versus system 2, right? So the stupid fast system is saying, okay, I'm just going to use physical spacing as an indicator of how I'm supposed to be doing things, even though I know formally, according to PEDMAS or my rule my rule whatever for figuring out how to do the order of precedence, that's not the right thing to do. And there would actually be a little bit of evidence, depending on how you interpret the evidence, in favor of this. That kind of evidence is that people are somewhat less influenced by spacing with increasing levels of expertise and with increasing levels of practice in our task itself. Okay, so here's what the results look like. One way of measuring your expertise is how correct are you on neutral trials. So if the spacing is equal around the multiplication and the addition, how correct are you? Some subjects are pretty bad, some subjects are 100% accurate. And then you can then, on the vertical axis, look to see what is their influence of consistency. How much better are they when we have consistent spacing rather than inconsistent spacing? And so the more a subject is influenced by the physical spacing, the higher their point will be on this vertical axis. And so there is a robust negative correlation such that the more they're correct, the better they are at algebra, one way of putting it, the less they're going to be influenced by consistency. One thing to point out, though, is that even for the subjects who are 100% accurate on the neutral trials, there's still a highly significant influence of consistency. We don't get any points below 0, and we're still getting a lot of people's points above 0. Okay, so that's one thing to say. About this interpretation, though, our preferred interpretation is going to be that we learn to do formal processing by offloading what used to be laborious, cognitive processes requiring the central executive processes, something you would associate with the frontal lobes, right? So it used to be that you'd use frontal lobes to force the order of operations of, okay, we got to do our multiplication before addition. But what happens over time is that we offload, not on the world in this case, but we offload on our perceptual system how to do this in the right way. So I consider this a cognitive illusion very much akin to perceptual illusions. Namely, this is going to be a strategy, this offloading onto our perceptual system, what we want it to do formally, is going to be very much like a perceptual illusion in that it's well accommodated to the real world. It can be trickable under experiments that perverse cognitive psychologists are likely to do. That's Diane, not me. So yeah, there's going to be situations where it can be led astray, but generally speaking, it's a good kind of illusion to be falling prey to because it means you're well adapted. So the point is that executive resources, applying this force of wills to do multiplication before addition, is going to be highly cognitively costly. So you're looking for ways to reduce that cost. So 2 points is, one, that we're structuring our math so that our perceptual strategies will work. Here's an example of that from work with David Landy. Everything I do is with David Landy here. And this is where people are writing expressions themselves to solve. So here we just give them the task, if you can read it up there, write the equation for, and then we write this out using our alphabet, 9 plus 12 equals 9 plus 3 times 4. And we look to see how they actually write out the equation, right? And then David Landy, bless his heart, takes digital calipers and he measures the distance between the different terms within this equation, right? And so in particular, he's interested in the distance around the equal sign, around the plus sign, and around the times sign. Obviously, I've picked a good example for my case. This is what we find, generally speaking, that people put less distance around the operators when they're writing this themselves, right, than they do around operators that have a lower order of precedence. So they're writing things in a way that is well tuned to their own perceptual systems, right? Here's data for this. I'll walk you through this a little bit. So on the vertical axis, a little bit idiosyncratic, is the fraction of the equal sign spacing. So we're going to normalize people to say this is the amount of spacing that they put around the terms that were around the equal sign. And then what we find is that the spacing around the plus operation is greater than the spacing around the times operation, which will, according to what we were just showing before, tend to make people do the right thing. They'll tend to do the multiplication operation before the addition operation. So, and you only get this, by the way, if you have mixed operations, if you have a problem that has both a plus and a times in it, because this is the situation when you'd really have to disambiguate it. Then it makes a difference whether you do 1 plus before another operation. 4 times it would make a difference. If you had another plus, it wouldn't make a difference, right? So the bottom line, literally, here, is that the notations that we're writing become tailored to our perceptual biases. So we end up producing notations that we ourselves are good at reading. Impressively, we do this without that much emulation. We certainly do this without very much teacher signals from our textbooks. We did a corpus analysis of many math textbooks for a variety of ages, and by far the canonical way of representing this is to have equal spacing around pluses and times. So people are discovering this for themselves. Okay, the other part of this is, so we're structuring math so that our perceptual strategies will work within our own lifetimes, and as Kajori, as a historian of mathematics, has shown, we are also doing this on the level of cultural evolution. So over time, our notational systems become better fitting to our perceptual constraints. The other aspect of this is that we're also structuring our perceptual processes so that the math works, right? And so that's the next thing that I wanted to try to convince you of. And so we call this notion RUPS, maybe? RUPAS? I don't know, I've never tried pronouncing it. But the idea is we're rigging up our perception and action system. It used to be RUPS, but we take completely to heart what the preceding speaker was talking about in terms of action as well. And so we're trying to rig up our systems to do what we think is the right thing. And so one way that this shows up experimentally is that we act in accordance with the order of precedence by training our perceptual attention. We move our eyes to the right place. Even when we're not moving our eyes, we're attending to the right kinds of information. So here is a simple study just looking at where people move their eyes when we give them simple problems like, what's A times B plus C? Or A plus B times C. And if we give people that first kind of problem, A times B plus C, what we can see here in the thicker black line is that the eye movements are originally deflected to the left side of space. And then later on, subjects pick up what's on the right side. Whereas if we gave people the opposite kind of problem, A plus B times C, then people are still they tend to look to the right side, and then they'll look more to the left side. So you're looking automatically to the part of the expression that you should be doing first if you're following the order of precedence. And this is true if we represent the times as an X or as a less attentional capturing kind of symbol, which is just the dot in the middle. Okay, so that's one kind of evidence. Another kind of evidence comes to us by the cognitive psychologist's ploy of the flanker task. The flanker task is even simpler than the task I was just describing. It doesn't require the subject to make any kind of mathematical judgment at all. They don't have to come up with an answer to the problem. All they have to do is say, what is that middle symbol? Is it a times sign or is it a plus sign? And they have one key for times, one key for plus. The correct answer in this case is times. The correct answer in this case is plus. The rest of the expression is just something that we tell the subjects they can ignore. And we give them trial by trial feedback again, so they know they can ignore it. Sometimes the symbols on the outer sides of this expression are pointing in the same direction as the middle element. Here they're not. Here the middle element says you should say times, the outer elements give you some priming for plus. Here would be a consistent trial where everybody is pointing in the same way towards times. Okay. The flanker task has shown reliably over countless years that there's a congruity benefit. Right? So if the outer elements point in the same direction as what you should respond to the middle element, then people are faster and more likely to get the right answer than if they're incongruent, right? And that's being shown by these 2 points here, the red circle here and the green circle here, are the incongruent trials. So those are lower. Oh, in this case, low is bad because this is percent correct. So people are pretty accurate. So we're only changing from 94% to 97%. But within that, you're getting an influence of the outer elements. But this influence is asymmetric in the sense that you're particularly hurt in this red circle over here, where you should have been responding to the plus in the middle, but the flanking distractor was a time sign. If it was the other way around, where you're supposed to pay attention to the time sign in the middle and the flanking distractors were a plus, then you don't get nearly as much interference, right? So time seems to attract your attention more than the pluses do. You're supposed to respond to the plus in the middle, but you're a little bit distracted by the timeses on the outside. We've replicated this. You could argue, well, but how do we really know that X's and pluses are really equated for visual salience? We're just recently, like a couple weeks ago, we've replicated this with materials that I shouldn't really present to logicians, especially when I say this. We give different subjects different orders of precedence. I'm sure many of you are shaking, right, with anger. We do debrief them at the end and say, yeah, and does have higher order of precedence than or. But for some subjects, we teach them that they should do the or operation before they do the and. And others, we teach them that they do the and before they do the or. And so we give them this different truth table, and you get different responses depending upon which group you're placed in. Right? And then you can give people exactly the same kind of flanker task that I was describing before. And the point is that if you are a subject who you're wrongly, unethically trained to believe that or has higher precedence than and, then you should be particularly thrown off by this kind of trial, where you're supposed to respond to and, but the outer elements should have acquired higher attentional salience to you. Okay, so those are the kinds of incongruent trials that I'm particularly interested in here. And the results came out, certainly the interaction is highly significant, so that's what I'm paying attention to. So overall, I don't really have a good explanation of why subjects are faster when or has a higher precedence than and, or why this or sign has a higher, is easier to find than the and sign. Oh, response time on the vertical axis. Here now, a low response time is a good response time. It means you're fast, right? And so, but the interaction, I do have an explanation for, and that's exactly consistent with what I was saying. The situation which is really, really good for subjects is if they're looking for an or among ands, and or during their training had a higher precedence. So that's a situation where they can pay attention to this or and they're not distracted by this thing because it had a lower order of precedence. You did that later. Okay. Going along with the action side now. So this is, again, echoing Professor Noe's talk pretty closely in terms of the perception and the action side of things. We're arguing that when you're good at doing mathematics, one of the ways that you get to be good is you learn successful actions for dealing with the objects. So we're arguing that mathematical reasoning employs visual spatial action processes that are particularly tailored to math. Here's one experiment that I thought is kind of cool in showing this, which is, I don't know, some of you will think that it's completely obvious, which is good, I think. So in this experiment, okay, so here's the background. This is probably not going to be legible by any of you, but take my word for it, there's actual letters and numbers up there. So you're asked to, that's a 6, so you're asked to say, what is the solution for y? Solve for y. Okay, so the question is 6 times y minus 5 equals 19, right? So you're supposed to solve for 19. We tell subjects that there's going to be bars in the background that are moving either left and right or up and down. Just ignore them. Okay, and so this is what it looks like. So you're solving for y. What we think subjects do when they become good mathematicians, at least some of them, is they use a physical transposition strategy. They're moving the 5 from the left side to the right side. Right? They're moving, and at the same time they're taking the inverse operation from minus to plus, and they're moving the 6 from the left side to the right side and turning it into its inverse operation of division. And that's the way they do it. And I mean movement in a fairly literal way here, that somehow it's either projected onto the screen that the subjects are looking at, or they're doing this in their mental imagined world. So in this case, the bars are moving in a consistent way with the kinds of transpositions that you would be doing if you were moving the constants over. This is a consistent trial too. You have to isolate the y, and the 8 and the 7 have to go to the left to do that, the same direction that the bars are. But this should feel some tension for you. This is an inconsistent trial where the 2 and the 3 have to swim upstream like salmon, right? In order to get to the right side, then the bars are going from the right side to the left side, right? And that's exactly, that's approximately what the results of the experiment showed. I don't know how much truth in advertising to do here. You're philosophers, you don't care about data, right? I should put it, truth in advertising, I should put in one note here. And so what I present here is exactly the effect that I'm talking about. So if the background motion is leftward, then people make a lot more errors when there's a rightward motion which is necessary to do the isolation of the variable. And if it's a rightward motion of the bars, then there's more errors when the things have to move to the left. Okay, so that's what I'm showing in the red versus the green. We only get that, interestingly, in cases where we have like y plus 2 equals 7, or y times 2 equals 7. That's the plus and the times here that you can't see. We don't get that kind of effect when we have minus and division. And I have an explanation that's right. David has an explanation that's wrong. And we can talk about that later on if you're interested. So basically you get more and more interference in this case with the objects moving faster and faster. Okay. The other, and this I think has some philosophical import that I find we need way more evidence on this. But the thing that I find most interesting about this is that the influence of motion, the difference between what I've circled as red and green, is actually greater for students that have more math experience. Okay? So here we're defining math experience by whether you, as an undergraduate at Indiana University, have had calculus. It's about a 50-50 split for students when they're taking this relatively introductory level psychology course. All of them have had finite, but some of them have had calculus, some of them haven't had calculus. For the students who have had calculus, they actually show a bigger influence of consistency. Right? And so this goes back to one of my main contentions, that you get to be a good mathematician by using these cheating strategies of like physically transposing the 2 from the left side to the right side. It's not something that you should be embarrassed of. It's a useful offloading from what would otherwise be laborious central executive processes onto your perceptual imaginal system. Right? So I think that's exactly the kind of pattern that we'd like to see, but my conclusions here are admittedly outstripping how much data we have. For this study it works. We have to see whether this is true for other kinds of perception action tunings. Okay, so I can skip some stuff. We've done more work. I did want to give a quick advertisement for a algebra tutoring system that we've developed. This is actually a suite of systems. We've developed this for 3 or 4 platforms now. I'm going to show you the iPad version because it's the most fun. So this is a system that we're very interested in testing out in educational systems where we're doing middle school, high school testing, and remedial college testing. It's something like 14 different classrooms now. For the iPad, it's called Algebra Touch. This is the research version, which will look a little bit different from the one that you get from iTunes. So what we're trying to get at is giving people familiarity with algebra and the perception action routines that you would do with algebra. So here we're trying to get them to have a physical intuition for what the correct groupings are and what to do operationally to algebraic expressions that you see. Right? So you'll see our sort of motivation here and the philosophy behind it. So here I've got my finger on the 1, and I can move the 1 around. Right? And through the commutative principle of addition, I can move it to the other side of the y, and the y will go wherever the 1 is not. right? One of the big principles that we're trying to teach is the idea of perceptual groups at multiple levels. So you can also take that entire y+1 group with your finger, and you can move it to the other side of the 2. This is the commutativity of multiplication, right? So you can have commutativity and working at any level of resolution. That's one of the big intuitions that we're trying to get at in algebra, that it's all groups made recursively of other groups, right? You can take, this is one I like. See, we've gone through many iterations of distribution. See whether this agrees with your intuitions. So to represent distribution of 2, the distributive law of multiplication over addition, as you move the 2 over, the 2 splits and clones itself into as many terms you have within the parentheses. Right? And so now the 2 has replicated, right? And so the opposite of factoring, or the opposite of distribution is factoring. So you can take the 2 onto the other 2 that matches it, and you can move it over, right? You could take the 2 over to the other side. That's what we're calling transposition, which is not how subjects are taught it, but you can cross out here. So you can cross out that didn't work by itself because they weren't the same term. But now that it's done the factoring automatically for me in this case, we can now cross out, I'm just taking my finger and swiping across the 2 2s, and that will work to simplify that. I feel a need to finish the problem now. All right. Okay, I'm done. Good. All right, so that's how that works. And I can present to you some of what the classroom data looks like on this. It's interesting. Yeah, I'll leave it at that for now. I think it is beneficial for people learning many concepts in algebra. It's not unmitigatingly good. Okay, I wanted to spend just a few moments talking now about cognitive penetration of perception. And I'm going to go back to Polishin's criteria for cognitive impenetrability circa 1984, a long time ago, where he argues that a cognitive function is cognitively impenetrable and hence part of the primitive functional cognitive architecture if, first off, you have a pre-change measure of what the function of the system is, and then somehow you're going to be changing the contents of the person's beliefs or their utilities, what matters to them. And then as a result of making that change, you now have a post-change measure of function, and it's different. If the function has changed in a way that is related to those belief changes, then it's been penetrated by cognition, and it's not then part of this, the functional architecture that we really care about. By this kind of account, I believe that perception of math notation that we've described here is certainly penetrated by cognition. One way of putting it, having utility for doing math leads to particular changes that we've been documenting, these changes in the perceptual grouping of notational elements. It alters your spacing judgments. It makes it harder for you to ignore multiplication signs rather than addition signs, etc. The question, I think, for Polishin, etc., is this a boring kind of cognitive penetrability, right? Boring because perhaps this is long developing rather than in the moment, in the processing of an individual stimulus. It's perhaps attentionally mediated, some of these, maybe, I don't know. And it's not online, right? So perceptual learning is sort of cast off as a less interesting form of cognitive penetrability for Polishin, because you could imagine, through rote, brute force training, somehow you're changing the feed-forward characteristics of this perceptual module, right? So, I mean, some things that I would point out about this, I'm particularly interested in chronic influences of perception. They're particularly powerful because they depend on a person's long-term goals. So, you know, going back to Susanna Siegel's examples, I may have a momentary goal of seeing somebody, Peppa, smiling at me, even though, because I want her to like me, even though she's got a neutral expression on her face. But there's a deeper sense in which that's not our long-term goal, right? Our long-term goal is to fit adaptively with our world and to really pick up things from the world. So if she's really frowning at me, I want to be able to see that, right? So I'm particularly interested in these chronic influences. The important point is that these kinds of perceptual learning effects I'm talking about are goal-related, and they improve the system's performance. The system is better at doing math because it's changing its perceptual system. It's not just neutral. The other thing I would just point out sociologically is interesting because this general argument that the system is an inaccessible module and so cannot be changed, that argument isn't even beginning to be tempting when it comes to the motor system. And I just find it really surprising that we find it compelling somehow when it comes to the perceptual system. Right? So we could easily imagine that there's motor modules, right? That there's a module that allows us to move our arm. And it's, I mean, the neurophysiological evidence is that it's just about as modularizable as the perceptual system. And yet we wouldn't say, oh yeah, because it's a motor module, we shouldn't be able to change it to fit our needs. It's hopeless for most. Of course we change it so that it does what we want. And I think that whatever intuition you need to see that should also be applied to the perceptual system to realize that even if you want it to be a module doesn't mean that you don't want to be able to tweak it. I'm interested in both non-strategic and strategic influences on perceptual change. One interesting disanalogy between this kind of random variation and selection that you get in evolution compared to perceptual learning is that humans are highly invested in improving their own perceptual systems, and they turn out to be amazingly resourceful in finding ways to improve their systems. So the title of this talk was something like hacking your perceptual system so that your performance is improved. There's two different senses of so that, and I think in the end I want to maintain both of them. One interpretation of so that is with the result that, right? And that would be consistent with random variation and selection, what like Gerard Edelman was proposing with his neural Darwinism, and that it certainly occurs. There's times when infants just randomly flail out their hands, and the very flailingness will sometimes give them a result that they like, and then they'll further reinforce that result, right? And as my colleague Esther Thalen and Linda Smith have argued. But I'd also like to argue that there is also a sense in which we improve our perceptual systems with the intention that they're going to get better. And this can be strategic at various levels of willness. So there's probably relatively few cases where we can intricately do brain surgery exactly on the visual system that we want to do. But there's many situations where it's semi-strategic. Not blind flailing, but myopic flailing, right? There's various ways we can do this. We can change the signal. Wine experts slosh around the wine in their mouth so that their perceptual systems will be able to pick up on the taste of the wine better. We squint so that we can see things more sharply. I don't know why that works. We look at the periphery when we're looking at a star so that we can see the star so that it's not falling on our cones, but it's falling on our rods, right? Weird cases of consuming vitamin A so that we can see in infrared, right? So we can, this is a change of signal, right? Polition, I think, says, well, that doesn't, that's not interesting. Of course, if you turn your head, you're going to change things. One important point to make here is that by changing the signal, you're also going to be changing what is learned. One of the facts that we know is that if you're attending something, if you're learning something, you're going to be adapting your neural system much more to that thing that you're turning to. Right? But there's other senses in which we're training our perception. We give ourselves, in many, many walks of life, we alter our training. We give ourselves spaced rather than mass training. We give ourselves simultaneous comparisons exactly to pull out important diagnostic features that we want to turn out. We give ourselves difficult cases. We give ourselves cases that we are particularly having troubles with. Right? So we look for minimal contrast in wine. We use words to help us figure out what are the important differences. How am I doing for time? 5 minutes. Okay. So I don't want to talk about most of these. So I think if people reflected on this, they would realize all of the senses in which we are hacking our systems to train our perceptual systems so that they do what we want. There's very different ear trainings that you would engage in if your goal was to be good at being sensitive to different intervals versus different functional pitch classes versus chords versus absolute pitch. In some ways, you give yourselves the opposite, orthogonal kinds of training if you wanted to train absolute pitch rather than intervals. Right? So we are deciding what we're going to value, what are our goals, and then we're going to give ourselves training that corresponds to this. There's nice examples from Nike's stroboscopic goggles to what Andy Clark was talking about yesterday, right? You know, these goggles that turn black every now and then, so that it requires the perceptual system to do more of the prediction. All right. So learning, I just came up with random examples, but learning to read a cut serve in table tennis, critically important, right? Because how you're going to respond to this is going to depend on what you think the person is doing by way of cut. It's not just association building, but you're actually doing causal model, physical modeling, at least to begin with, about what is the angle in which they're cutting and what you expect the ball's rotation to be doing, rotation that you can't see because it's just a small white ping pong ball. It involves theory of mind because you're trying to figure out whether they're trying to hide a cut from you by doing a reverse cut. So all of these things feed into how you're doing the training. Eventually, I think you want to make this as automatic as possible. But that automatic end result belies the fact that the training, the learning process is very much guided, right? Okay, so I'm not going to talk about any of these other examples. The point I'd like to say is that there's two general kinds of trajectories in learning that I think are completely consistent with each other. One is this strategic to automatic process that I was talking about, where you used to take something that required executive cognitive control and you offload it on your perception action system. And the other thing is a shallow to deep learning trajectory, which has been oftentimes shown for the development of expertise, where the experts see things more deeply. It's because I think oftentimes they're developing automatic strategies to look to the deep aspects. Okay, so the point is that it's going to be hard to say in many cases how much of these effects are this blind flailing that I was talking about versus this more myopic or strategic flailing. I think both of them are occurring. I guess the craziest idea, which would connect to what Clark and Chalmers have talked about by extended mind, is understanding the development of tools, representations, diagrams as another way of doing this. And so I'm a psychologist, so I guess I'm constitutionally predisposed to lump things together rather than make distinctions as philosophers do. So I'm attracted to the similarities between adapting your perceptual system and adapting new external representations to do things that would otherwise be difficult for you to do. All right. Conclusions. Perceptual and formal understandings are closer than you might have thought because perceptual processes and the objects of those processes, by which I mean these diagrams, these notational systems that we've developed, can be adapted to fit our formal requirements. A corollary of this is just because something is perceptual doesn't make it superficial, as Larry has been arguing for many years, with and without me, as Dr. Noe was arguing recently. The classic citation for Dr. Noe. And so this is the thing that everybody will disagree with me on, but I just thought I would say it anyway, just to aspire, to give you something to attack me for. As a cognitive psychologist who's supposed to be studying concepts, I have less and less idea of what abstraction actually means, even though I'm supposed to be using it. As I get more literal-minded and old, the best story I can tell for what we mean by abstraction is just the deployment of these trained and strategically crafted perceptual motor processes of the kinds that I've been talking about, working on notational systems, representations, diagrams, that are also strategically crafted to do what we want them to do. So that's an admittedly very deflationary idea about what abstraction is. Okay, so the final point that I'm saying here is that perceptual systems can change in numerous ways at numerous levels in terms of the brain, with varying degrees of intentionality or the deployment of strategy. And regardless of these various levels of intentionality, they can be guided to do the right thing, which means useful for achieving our goals. Okay, that's all.
Begin with Dave.
Oh, I was quivering with anger early in the talk when you were talking about the people doing it wrong with respect to precedence, for two reasons. One, the prescriptivist cultural imperialism of these committees. Algebra is a natural language found in the wild, and the practices of people's actual practices and grouping define the rules much more than the PEMDAS rule of some committee. But more deeply, I think, PEMDAS, when we look at parentheses, multiplication, division, addition, subtraction, what matters isn't the symbols. What matters isn't the symbols. What matters is the concept. You can write multiplication in different ways. It's not this. You can write it with an X. You can write it with a dot. You can write it with just by adjoining two things. Well, likewise, you can write parentheses in lots of different ways, bracketing in lots of different ways. I think, what we had up here was lots of different ways of writing parentheses. You can do it with this. It turns out there's a convention for writing the parenthesis operation, which is spacing. So I just resist the idea that this is all about the people are getting it wrong in these cases. There's just different conventions for bracketing, which might be perfectly correct. And all of this is in effect about the perception of bracketing. Yeah, right. So on the first point about doing things right versus wrong, I'm just going along with what our Western mathematics tells us, the one that we've all been encultured to, right? So, I'm not, again, making arguments about morally right. I'm just saying if we buy into these rules that I think most of us bought into, I think I even preceded the example by saying, according to math, what would you say is the right answer? So on the second point about the notations, I think there's a real sense in which you're right that you can represent brackets, parentheses, in lots of different ways. I think there's telltale clues within the notations that are very much grist for my mill, and which I think you alluded to yourself, that it's not a coincidence that the parentheses are curved inwards. I think that's a great perceptual gestalt cue.
that you're supposed to make a perceptual grouping around these things. It would be a perverse mathematics if the parentheses were faced in the opposite direction. So, I mean, to the extent that there are evolved notational conventions that go along with our perceptual systems, I think that fits really well with what I'm saying. If you're making the point that there's some generalization, so if we tell people, okay, now we're going to use an ampersand to mean parentheses, people can learn that. The question, to my mind, is how do they actually mechanistically implement that, right? Do they, and there's different perceptual accounts for how that would do. One account is by finding a similarity, a perceptual similarity between ampersands and parentheses. Another is by creating something like a lookup table, from a substitution, if you will, from one symbol to another symbol. But I think of those as still perception action processes, though. That's the claim. It's not that you have this somehow amodal generic parentheses out there. You do it by one of these other action hacks.
Is there any possibility of extending this sort of research to how we process natural language strings of words?
Yeah, so there is a project that I'm working on with Art Glenberg and David Havas, which is doing exactly the most brain-dead version of what I was talking about with spacing with natural language. And we're showing robust effects, exactly like you would expect. So that if you have a clausal boundary, but you have a big physical spacing between the words, it's much harder to process than if you have a small physical spacing. So that would be one application, but I'm sure that there's far more interesting generalizations of the perceptual laws of organization to reading, for example. I mean, it's obviously a case where what it means to be a good reader oftentimes is very perceptual. That's why we require so much experience and so much reading practice to, over 12 years, you're still improving in your ability to recognize individual letters, right?
Cool. So I guess my question is about the extent to which the expert perception elements here are, if you like, inextricably intertwined with what you know, and the extent to which they might be sort of slightly removable from that. So, if I'm put into an environment where I don't have the ability to write things down on the page, I seem to deploy the same body of knowledge in order to try to solve that problem. That might suggest that there's something that is available that's at a slightly different level there.
Yeah.
Or are they fully inseparable? I don't have an axe to grind on it. I just wondered if you thought there was an issue there.
Yeah. So I think that's a great point. So at a first pass, I think there's a sense in which one of the big worries about expertise is that you become blind to other ways of viewing your world, and I think that is partially true. So I mean, Rich Schifrin, our colleague back when you were at Indiana. So he's got these results that if they're used to looking for threes and now you're supposed to ignore threes, you can't help but pay attention to those threes. So that's the sense in which expertise does commit you to a particular way of viewing the world. But there's so I'm going to sound like the kind of people who say that all of the problems caused by technology are solved by more technology. So but I believe that for perceptual learning. So what I'd say is that the problems that you get from crafting your perceptual system in one way, that could be fixed then, are solved by other kinds of perceptual learning training. So one of the things that you can do is give people training for saturation categorizations versus brightness categorizations, as shown up there. They probably all look the same. And you can make saturation experts. If you just give them the saturation category boundary, then they'll get really good at that, and they'll tend to ignore brightness differences, even if they become later on relevant. But there is a way of creating experts that you pull apart the saturation from brightness dimensions, which is by alternating them, give them 100 blocks of saturation, then 100 blocks of brightness categorization, and then the hallmark of that is that they can now rapidly switch from a situation where categorization is relevant to brightness is relevant. And so I think there is a sense of expertise where an expert has better differentiated dimensional world, perceptually speaking, and that allows them to then selectively attend to those. Yeah.
Thanks. So I agree with you. It's important to stress the connections between formal systems and perception like you do. What I'm unclear about is what you mean by offloading the executive function to the perceptual system, because that seems to imply that the formal system could in principle be done without anything perceptual, but that can't be true. We couldn't do any of these operations without symbols to begin with. So why isn't what you're showing that it's possible for us to make different decisions about which symbols we use?
When I'm talking about offloading, I guess I do mean that something that used to require the online strategic deployment of strategies or rules now no longer requires that. The perceptual system is doing that for you. What I'm trying to say is that there's things that look and are designed to look like their formal processing that are now done by your perceptual system. And that will leave your central executive system available to do other kinds of formal processing. So there are always being something that's being done there, but the perceptual system is doing things that used to require formal processing, but no longer do. I mean, the other aspect of this is it depends a bit on what you're meaning by formal processing, because I'm very much talking about symbolic processing if what you mean by symbols, which I think is legitimate, is these notational elements. All of the processes that we're talking about in terms of the perceptual action system are on these notational elements. And if you're comfortable calling those symbols, then yeah, this is symbolic processing. It's a very different stance than what Newell and Simon used to talk about physical symbol systems, right? But I mean, so I think one way of viewing this is we're talking about really physical symbol systems because we're really talking about the physical spatial affordances of these symbols as notational elements. Whereas for them it was very important that these symbols were amodal, that they didn't have any link between the way that the symbol looked and what it was doing in the system. And they wanted to break that link on purpose because they thought that if you had the actual physical properties of the symbols influencing things, then you're unduly limiting what they're capable of doing.
So Jurgis is going to make a couple of brief announcements. Sadly, we have no more time for the remaining questions, but those who have questions can track Rob down. But it remains to thank Rob for a wonderful talk.
So I have two short announcements. First of all, those of you who are interested in